Continuous uniform random variables. Continuous uniform random variables. Okay, so x is distributed uniform with these two parameters, say theta 1 and theta 2, if the probability density function for it can be written as 1 over theta 2 minus theta 1 times the indicator function of x being between these two guys. Okay? And so what does that look like when we graph it? Well, let's say we plop down theta 1 right there and theta 2 right there. Okay, and so I'll go up to there and to there. I'll go across like that. Yeah, and like so. Yep. Okay, that's what it looks like. Oh, and how high is this? This is 1 over theta 2 minus theta 1. Yeah, we call it uniform because it's flat. It doesn't change. It's stationary on this interval. Okay, so that the chance that the variable falls between these two marks is going to be the same as the chance that the variable falls between these two marks, right? If you have two marks that are equally spaced apart, okay, then you have the same chance of the variable falling in there. It's flat. It's flat. Okay, now, just like with any kind of continuous random variable, the chance that this uniform variable falls between two marks A and B is simply going to be the area bounded by the density function between A and B, right? So, if I wanted to write the probability that x is between A and B in that closed interval, for example, this is just going to be the integral, right? This will be the integral from A to B of the density function dx. All right. So now I'm gonna write down my density function in the integrand there, which is 1 over theta 2 minus theta 1 times the indicator function of x being between theta 1. Oops, it's a little x between theta 1 and theta 2 dx. Okay. So, what does this come out to be? So this will be the integral from the maximum of theta 1 and A up to the minimum of theta 2 and B of 1 over theta 2 minus theta 1 times the indicator of x being between theta 2 and theta 1 and theta 2 dx. Now, how did I come up with these two things? Well, because see, in general, it may be that if I look up here, it may be that A isn't here between these two thetas. What if A is actually less than theta 1? What if A is down here? Then this integral that we're seeking is going to be the area bounded by the density function between here and B, right? So then in that case it would be, well, it would essentially just be this area, right? The area of this region in here. So then if I want to integrate from this integrate the density function starting down here somewhere, if A is down here below theta 1, then essentially, because the density function is 0 there, then I just need to start at the maximum of A and theta 1. Okay, and just integrate from here on up. On the other hand, if A falls over here to the right of theta 1, then I would just integrate from A to B, or again the maximum of A and theta 1 up to B. Okay, so that's why I've written that in the lower limit. Similarly, that's why we have this expression for the minimum of theta 2 and B in the top limit there. Okay, so now I'm out of space down here. I'm going to move up this way. Here we go. So all of this now can be written as So if I integrate that, I get I just get 1 over theta 2 minus theta 1, right? That's constant. That pops out of the integral. Go from the max of theta 1 and a up to the minimum of theta 2 and b dx, right? And so that's just it's going to be 1 over theta 2 minus theta 1 times the minimum of theta 2 and b minus the maximum of theta 1 and a. All right? Now, generally, though, we aren't going to be silly and pick a and b to be outside that interval. So, generally, this would probably be b and this would probably be a. So then, in such a case, when a and b fall right in there in between the two boundary, you can think of those as boundary points, and this is just going to evaluate to b minus a over theta 2 minus theta 1 if theta 1 is less or equal to a, is less or equal to b, is less or equal to theta 2. Okay? Very good.